Hi, I'm Ben-Yaakov. This presentation is entitled Deciphering the Operation of Flyback Converters' Active Clamps. Let me start off with a description of a flyback converter. Flyback converter includes a coupled inductor. This is not a transformer. Looks like a transformer. We have no other symbol for it, but it's a coupled inductor, meaning that energy is stored in it and then it's moved to the output. So this is a coupled inductor. There is a switch, and then there is a control that will turn on the switch and off. And when the switch is on, energy is stored into the inductor, and when the switch is off, the current will go out to the load. This represents the load, this is a filter, and this represents actually the load. Let me now go into a little bit more details about the DCM flyback converter, because we would need all these waveforms later on to understand the active clamp. So here we have the flyback, and now I'm representing it as a inductance, here LM, inductor, and an ideal transformer. This ideal transformer is transparent to power. That is, all the power coming in at a given instant is going out, save some magnetization current, which I'm not considering here. So this is an ideal transformer, which, by the way, has an inductances ideally of infinite value. So this is the inductance representing the inductance of this coupled inductor, and this is an ideal transformer. So when the switch is on, current is flowing through this inductance, charging it with energy, and then when the switch is off, the energy actually goes out by virtue of the fact that this LM now feeds the current, you might say, into the ideal transformer. Just read this way, and then the current will go this way. This is an ideal transformer, so that the currents are actually canceling each other as far as the magnetization of the core is going. Now there are some voltage stresses here. When the switch is on, there is a V in over N. N to 1 is the ratio of this transformer. This could be, N could be larger or smaller than 1. So we have here V in over N plus V out. So this will be the voltage across the diode when it's the off state. And here we'll have a voltage across the transistor when it's in the off state of V in plus N times V out. And again is the turns ratio. Now when the switch is on, current is increasing linearly, as it's shown here, because this is an inductor. There is a constant voltage imposed on it, so the IDT is constant, so the current is going on constantly, and when the switch is off, current is coming out, and then it'll go down in a constant rate. In this case, again, imposed by the voltage across the load. This is a large capacitor, so we assume the voltage here is about constant, and the inductance, which is reflected to the output. And then we have here a period of no current, and this is this discontinuous mode. That is, there is a period in which there is no current in this magnetization element. So this is the DCM flyback converter. Now, if you have a flyback converter and you have this coupled inductor, this is again a coupled inductor, there will be always leakage inductance involved. The leakage inductance represents the part of the inductance which is not common to the two sides, that is, inductance which is not coupled between the primary and the secondary. So we represent it as a series inductance, just an additional inductance, has nothing to do with this coupling between primary and secondary. Now, if we have current flowing here and the transistor goes into the off state, then current will start flowing, and in virtue of the capacitance that you have here, that's the output capacitance of the transistor, there might be some other capacitances involved, you'll get a spike. This is a sinusoidal waveform, and this spike might be very high, depending on the parameters of the circuit. So high that it can damage the transistor. So we can represent this situation by this equivalent circuit. This is the reflected voltage from the secondary to the primary, V out prime, we have the leakage, and then we have the capacitance, which represent the total capacitance in this vicinity. And as you can see, there is a resonant circuit here, and again, you might get a fairly high voltage depending on the initial condition and the values of the inductance and capacitance. So in order to avoid this problem or to combat it and protect the transistor, there is a need for a clamp. Here is an RCD clamp. This is the classical passive clamp, and the purpose of this clamp is to clamp the voltage so it will not go above a certain value. This is done by having a large capacitor here, which is charged. At a steady state, there will be a certain voltage across it, and when the transistor goes into the off state, then the current will go here this way, and the voltage will be clamped here. Now, what is really happening here is that the energy coming this way, this is the leakage in the leakage inductance plus some energy actually coming from here, goes into this branch, and eventually it's going to be dissipated as heat by this resistor. So energy that is stored here is eventually lost to heat. So this is a real power loss. Of course, it'll reduce the efficiency, and this is the purpose of the active clamp. The active clamp is meant to prevent this loss of energy, okay, that you'd have in the case of the RCD clamp. Another issue, which at the same time we are going to solve the problem of this energy here, which we are going to solve by recycling it. That is, we like to move the energy that goes into the capacitor back somewhere losslessly as possible, that is without losses if possible, or reduced losses. Aside from this major objective, we have another objective here, and that would be to achieve a zero voltage switching of this main switch. Now here's the problem. In the regular case, without anything else, we have the snubber here. Here is the snubber. This is where it is clamped to the capacitor voltage. This is the voltage, total voltage, that is the Vin plus reflected voltage. This is after the energy actually moved here. And then at the end of the current, that is when the current goes down to zero at the secondary, we would have oscillation here because we have an inductance, we have a capacitance, so this is an oscillation circuit, a resonant circuit. Now, at a given time, we are turning on this transistor again. This is the next cycle. Now, we can turn it on here, can turn it on here. This will be a nice place to turn it on. This will be worse because as we turn on this transistor, if there is a high voltage across it, there's no current, but there is a voltage across the transistor, this capacitor is charged. So if we turn on the transistor in here, we will discharge this energy we'll dump it into the transistor, and this is an additional cause of losses, of course, that it'll be nice to eliminate. So we would like somehow to avoid this situation, and one way to do it is to design the circuit such that it'll have a zero voltage switching. And here just the concept. We'll go into it a little bit later in more detail. The concept is that if we can somehow reverse the current here, then the built-in diode of the transistor will start conducting. Once this diode is conducting, we can turn on the transistor at zero voltage switching. So here it is. By some external source, you might say, this voltage goes down until the diode conducts. As the diode is conducting, we're turning on the transistor here at zero voltage switching, which is very nice. So the dual purpose of an active clamp would be, first of all, to recycle the energy here, and secondly, to somehow design the circuit that it will achieve zero voltage switching. Before going into the detail, let me simplify the circuit a little bit by changing this configuration into a simplified equivalent circuit. It'll be easier to explain later on. So what I did is the following. First of all, we have here already the coupled inductor represented as the inductance plus ideal transformer. Next, I'm reflecting sort of the output to the primary. Here it is, secondary to the primary. Here it is. So this is reflected by the current ratio. It's not important, the values here at this point. And the point is that we sort of eliminated this transformer, so we don't have to worry about current coming in, current coming out, etc., etc. This is a simplified manner. And also, let me just mention, although I'm not going into it, that in practical circuits, we would like to avoid some of the losses due to the voltage drop of the diode. For this purpose, we can include or replace the diode by a synchronous rectifier. Synchronous rectifier is actually the MOSFET that we'll put it here, such that when the diode is here, when the diode needs to conduct, it'll first conduct through the diode of the transistor, but then we're going to turn the transistor on. By this, the voltage drop will be low. Of course, we need a transistor with a small RDS on, so that the voltage drop will be low, and therefore the losses will be lower. So this is an addition to the whole thing. We can put a synchronous rectifier at the output here or here. Usually it'll be here because it's sort of close to the ground, secondary ground. In any event, this is an addition, and I'm not going to elaborate on it very much. One more point that I like to clear out, because we are going to need it, is the currents in a structure like this. This is again a coupled inductor. This is now the inductance, this is the ideal transformer, okay? Now in a coupled inductors, the energy stored depends on the current coming in, and the current of the inductance, the equivalent inductance of this structure is the current of the primary plus the current of the secondary. Note that both of them are going into the dots. It's not like a transformer. In a transformer, one is going in, one is going out, and they are actually canceling each other. Here, I'm showing the case in which two currents are going in. So the inductance of the structure here is magnetized, or energy stored by I1 plus I2. This is for a one-to-one, otherwise you have to take into the account the transfer ratio. Now, in a real case, like here, we are going to have this inductance. So this is the inductance which is magnetized. Now, it could be two currents, could be one current, either in the primary or in the secondary, could be two currents at the same time, or can be only one current. So that all these are possible because we are not talking about a transformer in which, again, energy coming in is going out by virtue of the cancellation of the current or magnetization effect of the current, while here we are storing energy. So now let's have a look at a couple of cases to understand it a little bit. I'm showing here a case in which we have a transistor turning on and current flowing through here this way, and in this case the inductance of this coupled inductance is being charged with energy, and this is the path of the current. Here it'll be shown this way. Here it is. This is the current of the inductance. Now if the transistor is off, the current from the inductance, you might say, goes into this ideal transformer. This is now a transformer. So current coming out here will be cancelled by current coming in. So this will be the directions, and therefore in this case this energy goes to the secondary. Here we're going to showing it this way. This was the initial current here, and here it goes like this, going to the. Let's have a look at a little bit more complex situation, which we are going to meet very shortly. And this is this situation. On the one hand, we have this inductance, this major inductance of this coupled inductor, discharging, you might say, into the secondary. Here we have the current going into the transformer, and this is the red one due to this current coming out here. But at the same time, we have a current going this way. And this current now is passing, you might say, through this transformer. So in this case, this is a transformer. So this current coming into the dot will be actually coming out of the dot. Okay, so this is the other path here. And we have now two effects. Obviously, there is one current here, and there's one current here, but they are due to two effects, you might say, depending on the situation of the circuit. Now you'll see here there's a current going in the opposite direction through the diode. Don't worry about it, because once the diode is on, then current can go two ways. Or you might say this current will reduce the amplitude or the magnitude of this red current. Now obviously, if this intends to be larger than that, it will not flow. We're not talking about this. Let's assume that this red one is larger than this one, so then this diode will just see a smaller current than this red current. This translates here into this situation. On the one hand, we have this red current discharging the inductance of this coupled inductor, and on the other hand, we have this current of this path. And of course, these are sort of canceling one each other, and you'll have the sum of these. Again, this red one should be larger than this other one. And there might be a situation, by the way, that these will be equal, and there will be zero current here, but there will be current here. We'll talk about it. Okay, so now I'm going into the real issue of active clamp. And this is the circuit of the active clamp. Well, it looks a little bit complex. Don't worry, it's really simple once you understand it. It's really a simple circuit once we understand how it operates. So we see here the equivalent circuit of the flyback. This is the inductance, the output section, the diode, the leakage inductance, the main transistor, M1 I'm calling it. And then we have the clamp capacitor. Notice there is no resistor here. In fact, in practical cases, practical circuits, we're going to put a resistor, but the purpose of this resistor, which will be large relatively, is to sort of discharge the capacitor in case of we have transients, and all of a sudden this capacitor is charged to a very high voltage, and we like to help the circuit to stabilize, so we might put here a resistor. So for the actual operation of the active clamp, there is no resistor here. And then we have an extra transistor. This transistor, we are using actually this built-in diode for the first instance, and in this case you see we have something like the RCD. This is the diode, this is the capacitor, except we don't have the resistor. The reason is that we are going to circulate back the energy, so we don't need to dissipate the energy by a resistor. So this is this auxiliary transistor which is put here. Okay, so then we have currents flowing in the circuit, and I'm showing here the current of the source. Notice that the positive direction that I'm showing here of this current, this is the current of the source, there's a power source here, is in this way, that is into the power. So meaning that in this case, actually power is transferred back to the source, and we're going to meet this situation. In the normal case, when we are delivering current from the source to the circuit, the direction will be in the opposite direction, but it is customary, at least in simulation, to label the current going into the positive terminal of the source as the positive current. So we have this current here. Now let me just state that what I'm showing and what I'm going to show here, first of all, is the basic implementation of the active clamp. The actual practical circuits are a little bit different. I'm going to talk about them, but I think it'll be easier if we just consider the very basic implementation. And in this case, this capacitor and this capacitor are assumed to be very large, so that the voltage across them is about constant, okay? So that in steady state, the voltage here is going to be constant. There is a question here, which is kind of a little bit of a mystery. Well, if there's no resistor here, how does this circuit know to stabilize this voltage here? Well, the reason is, I'm not going to elaborate on it too much, just to explain it in an intuitive way, that as it turns out that if this voltage is wrong, that is too high or too small, then the current will be unbalanced here, and it will tend to build back the voltage to the right value. So you don't have to worry about it. You don't have to sort of monitor this voltage, make sure it's constant. The circuit by itself, it turns out, has, you might say, a negative feedback to it, so that if the voltage is too low, it'll pump more and more current until it'll stabilize to the right direction. Okay, let me move now to the plots here, the time domain plots. I'm not going to go into the details now. I'm just going to explain what are these graphs, what are these pulses showing, and which we later on will discuss. So we see, first of all, the pulses to the gates of the two transistors. Now the red one is the main transistor. This is this one. The yellow one is for the auxiliary. Notice, of course, that there is a dead time between them, which is very important. We'll talk about it. And they're coming here in alternate fashion, except for the dead time. One is the complementary of the other. And then I'm showing here the voltage across the main transistor. This is this transistor. Obviously, it will build up when the gate is low. When the gate is high, transistor is conducting, and VDS is low. Okay. And then I'm showing here the voltage of the clamp. This is the clamp. This is VC. This is referred to ground here now. And then I'm showing VDS at the same time. Obviously, when the transistor is on, VDS is low. This is the main transistor. But when the transistor is off, this voltage will go up, 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 and will clamp to this capacitor. And as it'll clamp here, it'll be very, very close to VC. Okay? So this is this here. And here I'm showing the current of this switch, this auxiliary transistor. What we see here, that when the transistor, say, goes off, here it is, goes off, the main transistor, we expect this current to go this way, and this is what we see. This is negative current to the MOSFET, meaning that it goes this way, and then, as we can see here very nicely, it'll go back. That's what we want. We want this area to be equal to this area, because this is the current going to this capacitor. It should recycle here, okay? Then we see here the current of this source. Here we see positive meaning it goes into the source. That's bad news. We really don't want it. We don't want to recycle energy back and forth, because each time this energy is going back and forth, there are losses throughout the wires, the passive element, etc. So actually, one purpose of a good design would be to reduce this part as much as possible. This one, of course, we need. This is negative, this is this direction, and this is when the input is feeding in energy to the circuit. That's fine. Then we have here the current of the inductances. And here we see the current of the magnetization inductance. This is the current of the magnetization inductance, which is also shown here. This is actually the yellow one. Okay, this is the current here. When the transistor is on, obviously this current is building up. Here we see it, it's building up. When the transistor is off, then the current goes to the output, and as we have seen before, it'll go down. So this is the current through this inductance. Then I'm showing here the current through the leakage inductance. This is the green one, okay? When the transistor is on and current is going this way, these two are the same. That's fine. But then we have a situation in which they are not the same, and this is actually when energy is going out to the output. This now, the ID here, is the current through the diode. This is this current. And this current builds up when these two are different. And they are different because, on the one hand, this is going this way, that is this charging, the inductance is charging into the load, and then we have this current going through this way. I'm going to talk about it later on. Just here, this is just for understanding the waveform. So we have the two pulses, we have VDS, we have the current of the primary inductance, we have the current of the leakage by itself, okay? And then this is, by the way, the green one is the current of the transistor, this transistor, okay? So that when the transistor is conducting and all this thing here is going this way, we see it the same thing. And then when transistor is off, there is no current through this main transistor. That's not very interesting, but it's shown here. So we have the current here, we have the current going back to the source, we have the output current, we have the current of this transistor, and then we have the output voltage of the clamp, and then the VDS going close to it. So let's start out the story at a given point when we turn on M1. As it turns out, at the instant that we are turning on M1, VGS goes high, which is here, okay, this is, we see it here. I've put a blue color on the line here, on the pulse, this is here. It turns out that at this instant, the current goes this direction. I'll show how we arrive at it, but let's start with this point. We have to start somewhere. So we're starting here. So the current is now in this direction, no current to the output, just through leakage and main inductance. The diode is conducting, and we are turning on the transistor at 0 voltage switching. That's fine. That's what we want, 0 voltage switching at the beginning. And then the transistor is on. And of course, because we have a voltage here, positive here, short here, the dI/dt is in this direction, and eventually the current will change direction and start flowing this way. And this is what happens here. We have current through the inductance, current through the leakage, current through the transistor. This is the charging of the inductance. This is the on time. Okay, this is, here it is, and we are somewhere here with this voltage of the gate. Next, we turn off the main transistor. Here it is. We turn it off. This is the red one goes down. As the red one goes down, this current, which continues flowing, of course, because this is an inductance here, will find a path through this capacitor, and then when this voltage will eventually build up enough, it'll go through this diode. Okay, so when this is off, we have these currents flowing, and here is the direction. Notice that this current, per our earlier discussion, is going this way. Because we have an inductance here, you cannot change the direction of the current very fast. So this current goes on discharging, or this inductance goes on discharging, while at the same time we got this current coming out. Okay? So we have the situation, as I've said, that we have two currents here. One is this one, and one is this one. So we are here at this situation. Obviously, as soon as we turn off this transistor, the voltage starts building up. So this will be the turn off instant. Let me talk about it for a second. We have here a current. We have this capacitor. Here is the capacitor. This is the very beginning, and the diode is still not conducting. It'll conduct when this voltage goes close, of course, or actually passes a little bit the VC. Until then, these two currents are going through these capacitors. So we're going to have a certain rate. The VDT is I over total C here. And if C is large, relatively large, this is going to be fairly large or slow rise here, which is nice because we don't want the current of the transistor, which we are now in the process of turning it off, to overlap the voltage which is going out. Luckily, the capacitance, this is against Murphy law. Somehow Murphy here missed the situation, and we are saved here. Luckily, the capacitance of a transistor at the very beginning at very low voltages is very high. So we have here a relatively high capacitance, which slows it down. Now, we don't want these capacitance to be very large, because if they are, then we are going to have a problem when we are moving back to the zero voltage switching, that is when the voltage here is dropping down, because we'll have to move energy back to this capacitor, so we'll have to have enough energy later on in this inductance, reverse energy, to sort of charge these capacitors. So we don't want them large, and in fact, this is the good reason why we use gallium nitrate, or we like to use them if the price will be right, because gallium nitrate has low capacitances both for the input and output, while here retaining this feature. So at the very beginning it still has a large capacitance, but then it goes down, so the energy needed to charge later on the capacitance will be lower. So this is the instant of this VGS going down, the current passing here, eventually going into the diode. Now is the time to turn on this auxiliary switch, and notice we are turning it on under zero voltage condition, because the diode is conducting and we're turning it on, and still the current is going this way. And let's have a look at it here. We are at this instant here, the yellow one is the gate of the auxiliary diode, auxiliary transistor. Here it is. And then of course we have now the current of the inductance, main inductance, going out here, and we have also this current going this way. Notice that this is the current of the leakage going here. This is the current of the inductance. Notice that they oppose each other. So therefore, what we see at the output is just the difference between these two. This is the inductance, current of the inductance. This is the current of the leakage, and this is the difference. Yeah, it's rather poor. I'd like to make it larger, and we'll talk about it later on. That's very little. Also, here we see quite a bit of current at the beginning. Going back, I already talked about it. So this is now the stage in which the current is going this way. Energy, actually the leakage energy plus some more energy, is going into the clamp capacitor. Here it is. And eventually, again, because of the direction of the polarity of the voltage on the leakage, then it will reverse, and as the voltage here builds up, it will reverse the current, and the current will go back. Now notice that we have here, this is not a real straight line. The reason is that despite the fact that I've put here fairly large capacitor, in the simulation I've put here 100 microfarad, still there is some resonance here, so this is not a straight line. This is the resonance between this and this. So let's not worry about it. Let's assume that this is a sort of a straight line for the basic implementation. Notice that at the very, very beginning, as we have this current going this way and current going this way, because of these current being equal, because we started with this current here, then the net current through the output is zero. So here it is, at the very beginning we have zero current. Only when this current now is starting to go down due to the reverse polarity of the leakage inductance, we start to build up this difference, and therefore we're going to see the output. Next, this current is becoming smaller and smaller and smaller, okay? And eventually we reach a situation in which all the current is actually going in this direction because we have discharged the current of the inductance, and then we have the situation in which the two then are carrying this current which is coming from the clamp capacitor back here. So we are in the situation of a current going this way. This is a negative current. Here we see it, not very good, not very good. This already shows that you would like to have some sort of an adaptive control that will be able to start the next cycle somewhere here without waiting here with a passive duty cycle. And obviously, if you'll terminate this period here in this point, then the frequency will change. And indeed, with an adaptive control of this active clamp, you'll have a switching frequency variations. So here we are already in this situation, and the next step, of course, will be to turn off this transistor which was carrying the current. And then once we do that, we start having all these current coming back. We have through this capacitor current, we have through this capacitor, and eventually we're going to have through this diode. So this current, as it goes up, will cause this voltage to drop because we are now discharging these capacitors, and the voltage will drop. We see the voltage dropping. This is the VDS dropping, and eventually, of course, this current will pass through the diode only when the voltage reaches zero, actually a little bit negative, say -1 volt. And here we are now at this point here, and this would be a good time to turn on M1 under zero voltage switching. So this is where we began. So we went throughout the whole cycle of all these stages and went back. The disadvantage of this very basic implementation, which is like explaining the concept, is the fact that there's a lot of recycling current here, and this is something we don't want because it is causing extra loss. On the one hand, we recycle the energy, we have zero voltage switching, but then there's a lot of current passing back and forth, which will cause loss. One way to improve the situation is to use a modified implementation of the active clamp. This was published in a couple of papers, and here the difference is that we don't have the auxiliary switch on all the time, but rather for a short period just before we want to turn on M1. So in this case, what happens is that as we have this current through the M1 during the on time, which is like before, then we turn off M1, we turn it off, voltage goes up, current goes through the diode, like in the RCD case, the passive active clamp, and then the transistor is off. So there is a period there's nothing really happening here. And only before we want to turn on this transistor, we turn on this auxiliary one, current will flow the other direction, and then when we turn it off, it'll go through the diode, and we'll be able to turn the main switch under zero voltage switching. So that's what we see here. This is the auxiliary switch turning on for a short period of time, and of course the voltage here goes down, and then we turn on the main switch under zero voltage. Now the disadvantage here is that we are sort of leaving alone the drain of the voltage after the current going this way, leaving it by itself, and there might be some, as we see here, oscillations. So this is not a very nice thing, and this is why this method has not been really adopted. Before going on to more practical circuits, let me just point out that there is another way to add the auxiliary switch, which I'm showing here. This will be a P channel. This will be the source. This will be the drain. Therefore, the diode goes this way. Here's the capacitor. This is the clamp capacitor. So the current going here and charging this capacitor through this diode. And then we can turn on the transistor and the current will go the other way. It's exactly the same thing. The only thing is that being a P channel, it needs a negative gate voltage. So either we have a negative supply, or we can use this DC restorer, as it is called, putting a capacitor here in series. This capacitor will be charged to the positive value here of the pulses, and therefore when it goes low, it will show a negative voltage here. So this is one way to go. There is a disadvantage to this thing because during transients, when you need the fast changes of duty cycle, there might be a problem here. But this could be used, and in fact, there are many systems that are using this approach. So using P channel, the advantage here that you don't need a floating driver, that you don't need a, you might say, high side driver. Let me just point out here back for a second that when you have these two transistors, notice that they are here in series. So this is very much like a half bridge. So in fact, you can use a configuration of a half bridge with a driver for a half bridge for the low side and the high side. So this really is compatible with configurations that are being used for other purposes. So let's go now to a more practical circuit. In this case, the situation is very, very similar. It looks the same. The only difference is that this capacitor now is not very large. It is chosen to resonate with the leakage capacitance. So what will happen here is then the current is flowing here. After M1 is turned off, current flowing here, there is a sinusoidal waveform starting to form. Okay? So here it is. The transistor here is turned off, and a sinusoidal waveform is generated. Here we see it with the current of the auxiliary switch. This is the current of the auxiliary switch. There is a sinusoidal waveform going here. So it reduces the sharpness of this current. And as you can already see here, at the steady state, this portion here, which I was very much worried about, this is the portion of the input current. I'm not showing here the error. This is the positive part of it. This is the current going this way, is indeed becoming small. So we are not recycling that much energy because of the curvature of this line. And you can always also see it here. This is the curvature of this current due to the resonance phenomena. Now, since the output is really the difference between this and this, then see you have a larger output now because you have this larger difference. So this is very nice, and this is a way to go. Of course, you have to design it properly. And I should also say that the way to go is, I've actually fiddled around with the timing here so it'll look nice, but in fact you do need a adaptive control in order to turn on and off the switches in the right time, not to let it too long. So it'll end up with a variable frequency. In this case, however, typically in this configuration, you see that the current of the rectifier, I didn't talk about it earlier, let's talk about it now, is indeed starting with zero current, but then it does not end at zero current. So there might be some disturbance here as this current is turning off. This is the current of the output rectifier. So another option for the resonant active clamp is to use the resonance between this inductance and this capacitance rather than this capacitance. So in this case, this capacitance will be large so as to keep the voltage constant, and the resonance is between this and this. Now obviously, if you have resonance between here and here, voltage here will not be that stable. that is, you might have a higher ripple. This is why in this case you need another section of a filter here. I'm not showing it, another inductor and capacitor in order to filter out this disturbance. Okay, so we use this inductance plus this capacitance as a resonant circuit, and this is pretty much as before. You see that the curvature here, we have the curvature of the current going, it'll be like this through this resonant capacitor and inductor here to, this is like a DC, but as you can see, it's a very mild change here and makes this difference even larger. And also we can see that we can achieve here zero current switching of the diode. This is the diode, and the current goes down to zero before I'm turning on this transistor. So this is really a nice way to go, and there are controllers, IC controllers, offered by a number of vendors that use this approach. So this controller for the active clamp flyback will include whatever is necessary to turn on these transistors, and also to have adaptive control in order to switch it in the right time so as not to build extra circulating current. Also, I should mention that of course when the power goes very low, you have to go into burst mode, and the controller usually will take care of this also, make it nicely. So in fact, there's no way to operate a active clamp for a flyback converter without a dedicated controller. It's just impossible to build your own. It's just too complex a circuit for a discrete component. So this brings me to the conclusions of this presentation. What we've found that the flyback active clamp can indeed recycle the leakage inductance energy. There's no problem in that. They can also achieve zero voltage switching of the main switch, and in fact the auxiliary switch and the output rectifier. And that the bottom line is you really need a dedicated controller to implement adaptive control for optimum performance. You really need a adaptive control for the correct timing of turn on of all these switches. This brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.